Okay. And now I'll share the midterm. Just now, give me a second. Let me try and find that midterm. Okay, are you all seeing this? Just let me know. As I
Yes,
said, I
sir.
can't see the chat, so you have to talk.
Yes, sir.
Nice. Okay. All right. So I'm assuming that all of you were able to retrieve your midterm as well. So because I have left it in the office, in the department office. So if you don't have it, go and collect it. It's yours. All right. And then you'll see when I'm going through the solutions here, something that I mentioned to you all in class, that sometimes I do the questions and do some solutions and then vary the questions a little bit. So you'll see some notes here, and you'll see, and I'll comment on two other questions that I changed for you. And as a result, I have a couple of extra marks for people going through as well. All right. So question one was the one that gave most people, well, it was the largest component of the midterm in 30 marks. So it was a third of the marks coming here. And it seems to seem to have given everyone, or most people, the biggest set of problems there. So I put a hint here, which is typed in the midterm, that I calculate all the voltages and currents first to save time, right? I have a page that I will put up with the solutions here that tells you exactly how to calculate everything. But if you hold on, I'll bring up a small presentation, the same revision presentation here from last time, and right, okay, here we go, right? So on this slide, and I'll post this as well, here are all the voltages, currents, and resistances in the for that particular problem. Now, if you all are, I don't know if you all were some of the students that had issues with this or not, but right now I'll just pause. Anybody has an issue or had an issue going through this?
You meant for the exam, so yes,
Yes,
like right now.
in the exam itself. What was the issue, or what was the main problem that you had?
Well, for me, so I'd mostly practice like doing the unregulated or regulated components kind of separately. I didn't
Mm-hmm.
practice like doing a whole design yet. So when I saw that question, I realized that since I didn't practice doing an entire design, it's better for me to do the other questions and try to come back to that at the end.
Okay. Well, what I'd suggest, anybody else, Nathaniel, Liana, you all have any issues with, or had any issues with the problem itself?
So for me, not really. Is well, most to do with that. Like I worked on the parts that I knew I could have done, but then similar to Vidal, like I came back to it at the end and I just ran out of time to finish it mainly.
Mm-hmm. All right. And Liana, you all right? Or you have any particular areas?
Same thing as Nathaniel.
Oh, okay. Nice. No problem. All right. Okay, so what I have here, all the answers. As I said, I'll put up my working for it. I am not so interested in, as I told you, all the algebra of getting to the answers, but in the approach. And that is why in the midterm, I put the hint to calculate the voltages and currents first. Right? The voltages were very easy. So for instance, V2, um, well, the V in, there were two little questions about that, V in max and V in min, and I'd given you it here. So it should have been fairly, just let me get a different color here. It should have been fairly straightforward because I'd given this on the diagram like this. So calculating this value on this one should have been relatively easy. Okay? Because you know V out, and this is 1 ohm, and you know that the current is 2 amps, so the voltage drop across R4 would have been 2 volts, and if here is 5, then V2 is 7. Okay? And then you know that the diode is 2 volts, so here's 2.7, so V1 is 2.7, right? V3 has to be 0.7 volts more than here, and if here is 5, then V3 has to be 5.7. Okay, and the other missing one would have been V4. Is there a V4 somewhere here? Right. And then once you had that, then the currents themselves, I gave you the idle currents, and then everything else was just a question of using the currents and the HFE or the beta for the particular transistor. So you'll follow it through and see what I have. And if you get stuck, then as usual, what I was telling people is that if you still can't understand anything, send me the question, or the next time we meet, and we have other sessions, at least one other big session coming up to review. Okay? So we'll go through that. Let me just share the other, right. Okay. So the rest of the midterm, so this is the page here with all the calculations in it. All right, and you'll follow it through if you had any issues. All right. This one question 2 and question 3. Notice when I wrote the question, I didn't have this thing about a 1 volt peak to peak square wave. I had an input, and I thought it would have been easy enough to read from the graph here that the value. Let me see if I could get a pen here. Right, the value here, right, was easy enough to recognize as about 1 volt. But then I went and put 1 volt peak to peak in the paper when it should have been 1 volt peak. All right, so some people got the correct answer. Other people had plus or minus 2.5 volts here because the op amp was an inverting op amp. Okay, so I have a couple of extra marks in the bag for you all. And when I'm tallying everything at the end, if people need the marks, I have 2 extra marks to give everybody. I have a notation of who got 4 out of 5 and so on. All right. The big thing here was the inverting amplifier, and here was the non-inverting. Right? Same value resistors, but in the case of the non-inverting, of course, the gain will be 6 instead of minus 5. All right. This question 4, I mentioned in class that I ended up giving everybody the marks for it because the formula for calculating the 2 thresholds in the notes, originally the formula had R1 over R1 plus R2, whereas it's supposed to be R2 over R1 plus R2. Some people recognize that in the exam and got the correct answer. Other people follow the notes and then realize that, wait a minute, the threshold here would be like 9 volts or something. So therefore this signal, the signal, no way the signal would be able to switch if it is working. Right, so I ended up just to be fair to everybody, I gave everybody the marks for the part. All right, so I got 10, basically 10 easy marks going here. This question, I wanted people to, well, first off, half of the answer was if the gain, if AV was supposed to be 9, then the ratio between the feedback resistors and the gain resistor was going to be 4. And then I left people a number of ways. You were free to do it. I had 4, if the gain was 4 and you only have 100K resistors, then if RF was 100K, then you had to have 25K here, which means that you had to have at least 400Ks in parallel. Or as some people did, they put 100K here and 400Ks in series. Okay, so there were at least two simple variations of that. And of course, to draw the circuit and label the values. That's where all the marks came from. All right. Anybody had any issues with that, or did it? Any of you all did it differently than that for some reason?
No, sir, no issue.
Okay. All right. This
Okay, so
one was exactly from, pardon?
I just
Nathaniel.
have a question about the last one, like question 5. So when they said like that you're given a circuit below in figure Q5, which it cannot change, additional op amps and a supply of 100K resistors. That part doesn't mean like you only use 100K resistors, so what you're adding on.
Correct. Right. So whatever values you need to calculate, the only thing you have in store is some extra op amps and 100K resistors. You don't have any other value to play with.
Okay. Thank you.
Right. Okay. This one was exactly from the notes, except that the diodes here, when we did it, we had the diode the other way wrong. Right. So just it's kind of hard to draw with this thing. But anyway, our diodes were going this way in the notes. So what happens, it meant that the polarity of the output signal was the opposite of what we did in class. Okay, it's still an inverting half-wave rectifier, but the waveform is what we have, what I have shown down there. Okay. Some people put the one from class and so on. So if at least they recognized that it was an inverting half-wave rectifier, you got some marks for it, right? But to get the full marks, you really have to realize that the two diodes were flipped around. Okay, so always watch that. Whenever you have a circuit diagram, not only here, right, or you might be reading a description of something later on, just watch to make sure that the orientation of the components are how you are accustomed seeing it and not the other way around. Okay? And then question 7. All right, this was, I gave you a stable. This was straight from the notes itself, right? So it was on a stable. You calculate the thresholds again by the potential divider here, and because R1 and R2 were equal, then this thing was powered. I think it saturates at plus or minus 12 volts, so that the upper and lower threshold were 6 volts each, which is what we have here. Okay, and the frequency, you went back to the notes to do it. The notes tell you how to get the period, so the frequency is 1 over that. And then I wanted a label diagram, so I expected people to show me their thresholds, to show me the square wave, and to show me the times on it. If you just sketched it and the shapes and so on, you got a couple of marks, but there were some, you notice about half the marks were coming just from drawing that diagram with all the information on it. Okay, so all essential information. If ever you see a question that is asking you to draw a diagram or a sketch, give me a fully labeled sketch. Okay, you'll see some of them appearing in like the past paper questions and so on. All right. So essentially a very, very, very straightforward exam. And if most people had done the work, then they would have been able to pass it. So it was a little bit disappointing because of how easy it was. And I gave you 10 marks. The two op-amp questions were a giveaway of another 10 at least. And they really, the ones that you would have had to work with the power supply, of course, a third of the marks came from that. And then this last question here. All right, but it should have been passable. I don't think there was anything to justify the kind of marks that I saw. Any comments on this or questions that you all want to ask on your own performance at this point? Assuming that is something that's shareable.
So I have a question.
Yeah.
Question 1 could come back in the final.
In the final, yes, I could ask you everything because the midterm is not a must pass. Okay, it means that I could ask you things again in the final exam. If here was the only place that I was asking you that, then I would have to make the midterm a must pass. Okay. So in theory, everything on the midterm could come back in the final. The final is testing the entire course. The midterm only tested the first couple of things that we did in the on the course content. Okay.
So thank you.
Right, and there were 5 major topics that we did. Remember, we did the power supply, the sinusoidal generators, the waveform generators, the active filters, and op-amp, general op-amp applications, and then a couple of smaller topics that we did with the A to D conversion and the environmental impact of electrical and electronics. Yeah. Right, so that's that. Let me problem set 3. Let me just see if I can run through that with you. Just the solutions which are all in the notes. There we go. All right, so everything here about problem set 3, it is a good one to help you revise the sinusoidal oscillators on topics. So use it like that, like short answer questions to help the understanding the material. So like question 1, and you will see this in some of the past papers as well. What do you understand by the statement sinusoidal oscillators need to satisfy the Barkhausen criterion? Okay, check the notes. Remember, the Barkhausen criterion is a 2-path thing, that the gain around the loop is positive feedback that we're dealing with. So the gain around the loop has to be 1, right? The magnitude of the gain, and the phase change around the loop has to be 0 or a multiple of 2 pi. Okay, and everything else, everything that is done with the oscillators to try to make those 2 things happen. So the amplifiers give you the gain, whatever is the RC circuit is doing. The amplifiers provide the gain to make sure everything is 1. And then whatever the RC network is doing, the amplifier also provides the phase change to give you that 0 or 2 pi. Okay. Question 2 again, show the transfer function for the Weinberg oscillator is a particular, well, that one there. Remember, I told you that in the revision class, you should be able to sketch the Weinberg oscillator, or at least the Weinberg circuit, and then it's an impedance divider, right? It's a Z1 and a Z2, and if you work out the voltage division across that network, you get the transfer function looking here, looking like what we have there. And if you want to find out the frequency of oscillation, then you substitute S equal to j omega into that thing on top there. And then you find the value of omega to get rid of the imaginary part of that transfer function. Okay? And then question 3, of course, if you want to design it, there are 2 resistors and 2 capacitors that are equal. And I always tell you, if you're designing a any of these circuits where you are resistors and capacitors, you choose the capacitor first and calculate the resistor. All right, because capacitors, you don't have that wide a range of values to pick. So you pick a capacitor value and you calculate the resistance. Okay. Question 4 is a phase. Well, we did 2 networks. We did a phase lead and we did a phase lag, right? So check the notes to see which one is which one here, right? The difference between the phase lead and the phase lag is that the resistances and capacitors swap place. So in one of them, the capacitors are in series and the resistances go to ground. In the other one, the capacitances go to ground and the resistances are in series. So it's you need to identify which one is which and memorize the transfer function. You could derive it, and I will put up a version of the solution there for that. I think I have it in the past paper solutions or the revision problem set solutions here, just to let you, if you want to try it. It's a good way of memorizing it. If not, just remember the formula. All right. This one is actually a little bit easier because the filters, the R's and the C's, let me see, right. In this case, the R's and the C's here are all isolated by the op-amp. So these three op-amps, because they are what do you call it, voltage followers, essentially separate each RC section from the other one. So so you could calculate the transfer function for one here, and then the transfer function for all three of them, this one, and this one, will be the T1 multiplied by T2 multiplied by T3. And since they're identical, is the transfer function cubed. And then just to calculate these two values here, A, RA, and RB, the same process. You substitute S equal to J omega in the transfer function that you got, eliminate find out the value of omega that makes the imaginary part, the J part of that transfer function, 0. And then when you substitute, that will give you this, right? And then when you substitute omega 0 into the transfer function, you will get a V out over Vn equal to something, minus this, minus that. I think in this case is going to be -8, so that the gain of this amplifier has to be 8. In other words, RA, and it's an inverting amplifier, so RB has to be 8 times RA, whatever the values are. All right? It's straight from the notes. This one is easy to derive. Okay, it's very easy to derive. So you have to do it. This one likewise. This is also three separate circuits here. So all you need to do is to calculate this is like an inverting amplifier, except that instead of just a simple R feedback and R input, you have two impedances, a resistor in parallel with a capacitive impedance. And once you get the value of the transfer function for this block, is this by this by this. Okay? This is the oscillator. This gives you 3 sinusoids that are shifted by 120 degrees apart. Okay, so you get one coming from V1, one from V2, and one from V3. And the notes has the slides have a printout of the type of waveform that you get, right? And again, once you get the transfer function, you substitute S equal to J omega, and then you see the value of omega that makes the imaginary part of that transfer function disappear. Okay, and the last question here, why do the oscillators require gain stabilization? The Barkhausen criterion, we said, requires a gain of exactly 1. In order to make the oscillator start working, the gain actually has to be a little bit bigger than 1. But if it keeps at bigger than 1 once the oscillation starts, it keeps getting bigger and bigger, the output, until it saturates. So what you need is just some type of circuit where the gain is slightly larger than 1 to get it going. And then as you approach 1 and the thing is working, to start backing off the gain to less than 1, and then it goes back and forth, back and forth. And we saw a couple of examples of that. All I need you to know is to answer why we require it, not necessarily the circuits, because the circuits themselves, there are many, many circuits. And we looked at one, in fact, we looked at 2, 3 versions of them. Right, the one that use the thermistor or the sensitor, the other one that used a little like a feedback power supply that produce a negative voltage through a field effect transistor, and then the last one that I showed you that you could use the Weinberg was to use a pair of Zener diodes on the output, And what that does is that as the output starts to get close to saturation, the Zener diodes start to kick in and bypass the output resistance and convert the waveform into a sinusoid. It prevents it from going past whatever the voltage is on the particular Zener diodes. All right. So all of these answers are in the notes. Everything is there. Is there any particular issue that is troubling you all about these topics or this topic? Anything that you want to clarify?
Not right now, sir. Well,
All right. Okay. All right. Well, that let me just stop the recording here for the time being.